Hi, math fans. Today we're going to discuss Mat 181 pre-calculus trig, section 3.2, applications of radian measure. So what we're going to do in this section, we're going to talk about two things. We're going to talk about the arc length of a circle, try to develop how to find it, and then we're going to also talk about the area of sectors of circles. So there's two main things we're going to discuss: arc length and variations on that, and area of sectors in a circle. So what are we talking about? Okay, let's suppose we have a circle here, and we have a radius from here to here, right? And we have an angle, theta. And what we want to do is we want to find this distance. This is what we call the arc length. This distance we're calling S. And that's the distance. Well, it's not exactly a straight line. It's got a little curve to it, huh? And we're trying to figure it out, what that length of that piece is. So think of this as a pizza. We're trying to find out what's the distance from here to here of this pizza. Well, fortunately, there is a formula for it. This length right here, S, is equal to the radius times the angle, theta. So it's a pretty easy formula, S equals R theta, but there is a catch. Theta must be in radians to find this distance. So theta here on these kind of formulas has to be in radians. So let's try one and see how it works out. Okay, so this is on page 101, and we have this problem. It says circle having a radius, let's call this a radius of 18.2 centimeters. And we want to try to find, it's intercepted by a central arc. This is a central angle right here because it comes from the origin. And it has to, we want to know what is going to be the arc length if this is 3 pi over 8 radians, abbreviate. Okay, so how are we going to do it? We're just going to plug it in. S equals, that's what we're trying to find. The radians are 3 pi over 8 times 18.2 centimeters. So in this case, we're going to use pi as being 3.14. And we're just going to calculate this out. Or we can use our pi key, probably a little bit easier. So we're going to hit, let's turn on our calculator, clear it all out. We got 3 times pi times 18.2 divided by 8. And we come up with 21.44. We'll carry these always out 2 decimal places, centimeters. 21.44 centimeters. So just make it easier on you. We just always carry them out 2 places. Okay, in example B, we're going to do the same exact thing, only this one they try to make it a little trickier on us. The distance again is going to be 18.2. That's going to be the radius. So let's write that down. The radius is 18.2, but our theta is going to be 144 degrees. So first we have to convert that over. So how do we do that? 144 times, what was it? Pi over 180, because we want to convert over. So that's 144 pi over 180. The book says we can actually reduce this down. You know, you could use 144 over 180 because we're going to use a calculator anyhow. So let's just keep it the way it is. Let's see what we can do. The area that we want to find the length of this distance right here. So S is going to equal, what is it going to equal? 144 pi over 180 times the radius. The radius is 18.2. And we'll see what we come up with. Let's clear this out. 144 times pi times 18.2 divided by 180. And I came up with 45.74 centimeters. And so that's the distance of our arc length. Pretty easy, huh? And like I said, if you wanted to reduce that down, it might be easier numbers to work with, but still will come out the same anyhow. All right, let's try another one here. Let's try the distance between two cities. Interesting. So it says the latitude gives the measure of the center angle with vertex at the Earth's center, with initial side goes through the equator and whose terminal side goes through a given location. Reno, Nevada is approximately due north of Los Angeles. The latitude of Reno is 40, LA is 34, and the N means it's north of the equator. The radius of the Earth is 6,400 kilometers. Find the north-south distance between these two cities. So what we have here, let's draw an axis here, is the Earth, okay? And the distance from the center of the Earth to this point on the equator here is 6,400. And we have a circle coming through here, kind of like that. And up here we have Reno, Nevada, and Reno is from the equator. Just put an R for Reno. That this distance right here, not this distance, but the angle is 40 degrees. And the angle to LA from the equator is, they say, 34 degrees. So the angle inside here, this would be the area, this is the sector of a circle, and what we're trying to do is find this distance S between them. And theta itself is going to be the difference between these two. Theta, I'm going to write it here, equals 40 degrees minus 34 degrees is 6 degrees. That's what theta is. So it's just a matter of putting it in to our formula, but this is in degrees, we need radians. So 6 times pi over 180 is going to give me pi over 30. All right, now we're going to calculate out of the sector of the circle, this distance right here. The sector of the circle, or the distance, in really the straight line or in a curve is pretty similar to each other. They might even be equal. So the sector of the circle equals theta times r. Sector of the circle is not 6 degrees, but pi over 30 times r, which is going to be, what is r? Well, r is the same distance here, 6,400. I mean, if this is r, then this will also be r, the distance. This is Reno, not r. Okay, so the distance is that, and we should be able to find a little s right here. And so that's going to be, let's just use our calculator here, pi times 6,400 divided by 30 is 670.21 kilometers. kilometers, I think. They rounded off to 670, but we're a little bit more accurate. And we have the distance. So pretty cool. So what we wanted to do is find it. We wanted to find theta, which is right here. We wanted to find that angle inside here, 6 degrees. And then we do the radius. And once we knew that, we changed that to pi over 30. So we got pi over 30 times 6,400. And we're able to find the answer. Okay, let's look at example 3, see where you get confused on this one. Find the length using S equals R theta. Well, we just did that. Okay, this is rope is being wound around, edge round with a radius of 0.8724 feet, 25 feet, and how much rope will be round? We're going to wind up and through an angle of 39 degrees and 39.72 degrees. So basically, it's just our old formula. They made it a little bit more complicated. You got a little drawing here. And this angle right here is 39.72. And we're trying to find, let's extend this a little bit more, that they're putting some rope around this. But it looks like the rope is starting right here. So we're actually going from 90 degrees, 39.72. We don't need this whole distance. Just from here to here is where we're winding up. So the sector, the distance S, is equal to theta, which unfortunately is in degrees, so we got to change that to radians. And then what is the radius of this? The radius is going to be 0.8725. Okay, so that's our 0.8725. And theta is going to be, well, let's just do it this way. This is going to equal times pi over 180. We could do it separately, or we could just put that into our formula. So let's just put S equals this angle, which is going to be in radians. So we're going to do 39.72 times pi, because we don't need the times in there, over 180. So we could just multiply out this whole mess and see what we get. 39.72 times pi times 0.8725 divided by this whole thing, 180. You could do it in little separate sections or whatever, but I just did it, the whole thing across. 0.6, and we said we'd just go out 2 places, so it's 60. And this was in terms of feet. So less than a foot, 0.60 feet of rope. All right, try another one here. Next example. It says 2 gears are meshing. The small gear drives the larger one, is shown in the figure. This is example 4. This was example 3 we just did, 4. The smaller gear rotates through an angle of 225 degrees. Find how many degrees the larger one will rotate. Okay, so again, we're going to use our formula. S equals R theta. Okay. S is okay. Let's see what R is. R is the radius of the small little circle, which is 2.5. Theta, the theta is going to go through 225 degrees. Huh? So would this be 225 times pi over 180? So that should give us that distance that the small circle is turning. Let's see if that'll work. 2.5 times 225 times pi. We can multiply all this out because we're not doing any addition. If we have addition, then that's going to mess us up. I get 9.82. Okay, a little different from the book. The book kept it in things. Now it says we want to get the meeting of the two circles. We want to, I guess you got this gear here and this gear here. And we're trying to find out this distance right here where they're meeting. So we're going to use the formula again, r theta. Okay. But we know the distance, 9.82. We're trying to find, what are we trying to find here? We're trying to find the angle at which this is going to happen. We know R is the big circle, which is 4.8, and this should give us theta. So we're going to take 9.82 and divide it by 4.8. We actually have this distance. We're trying to find the angle in here. That's what we're trying to find. Oh, confusing. Okay. We put the 4.8 here too. All right, so let's try this and see what we get. It may not come out exactly the same as the book because we rounded it off and we don't even get, wow, 2.05. Okay, that doesn't look like their answer at all. But remember, this is in terms of radians. Now we got to convert that over. So 2.05 radians equals times 180 over pi should give us our answer. So 2.05 times 180 divided by pi equals, and this should give us our angle. And how close did we come out? 117.45 degrees. So pretty close. They said 117, kind of rounded off. So it was pretty darn close to what they said. Just remember that this is in radians when we're working in here, and we wanted the answer in degrees. So we had to convert back over to degrees. The last thing we're going to do is look at the area of a sector of a circle. A sector circle is kind of like eating a pizza. How much area is there inside this piece of pizza? So to do this, we have to kind of know the angle. And I'm going to use the one out of the book, except they're using a different thing, but it would work. So what is the formula, first of all? They use a fancy little gizmo for area. You can just put A equals, it's kind of like the area of a triangle. What is the area of a triangle? 1/2 the base times the height. See? So you got this, and what's the area of a circle? Pi r squared. So you're kind of combining the best of both of these. It looks like when you put these together, you've got the r squared, you got the theta, and you got the half. So it's 1/2 r squared theta. It's kind of like putting them together. You've got an area of a circle, pi r squared, you got the area of a triangle, and we can kind of work out this formula, but we're just going to take the book's word for it. So again, on all these problems, theta has to be in radians. Very important, it has to be in radians. So this is 15 degrees, right? We're going to use the one in the book. And we have a distance here of 321 meters. It was a huge piece of pizza. This is also going to be 321, 321, 321. Anyhow, the area is 1 times 321. We could either put in the 15 now and do the, well, let's just do that. Let's say we did this. This is over 2, 1/2. And then this will be 15 degrees times pi over 180. So we've got 321 times 15 times pi. And we're going to divide by, we got 2 times 180, so we're going to divide it by 360. And we come out with 42.00. And we didn't get the right answer. What happened here? Oh, pi r squared. Let's put the square in. Let's recalculate it. That seemed awfully small. Okay, 321 times 321, or raised into the second, times 15. Let's see if it makes more sense now. Times pi divided by 360. Looks awfully big, but apparently that's what they came up with too. 13488. They came up with 13500. Might be a rounding, but that looks pretty close. And this would be meters squared. Meters squared. So don't forget to square this, see? Because we're used to just using r theta, and now it's r squared theta divided by 2. You know, you can use this variation on the formula. Instead of r theta, r squared theta, and then you divide by 2. Area of a sector of a circle. So try those problems, try some practice on these, and see how it works out. I hope you enjoyed the video. I'm going to have trouble ending it. Here we go. Adios.